Welcome to Lecture 7 of the 6th week of the course in machine learning. In this lecture we will talk about some examples of associative memory, Hopfield networks, and Boltzman machine, and a few other approaches. As you can see from the map of material this week, we are now here. The coming lecture will then, after this, we will turn to something called convolutional neural networks before we finish this week. A Hopfield network is one approach to the realization of associative memory. It is an instance of the subcategory of association memory called auto-association memory, which, if you remember, is the situation where you look at a certain object, you have a partial description of that kind of object you're interested in. What you do is you, as like in a query fashion, put in this partial description, and the system is then able to provide you through the call the full description. So in a way, this kind of system primarily completes partial descriptions. It's not likely to give you anything more, anything wider, anything outside the actual domain. So a Hopfield network is also considered to be a recurrent neural network, even if it's not able to handle temporal sequences, in the sense that in every iteration, in every training, for a Hopfield network, you, in a way, define statically the inputs to the networks based on that particular data item. In other RN, you're able to have a sequence of items that constitute one single data item, and being able to handle that in the sequence. This is not the case with the Hopfield network. However, Hopfield network has states, and it also has cycles in the network. So because of that, it's counted as a recurrent neural network. However, it's more natural, I would say, to primarily classify Hopfield networks within the class of associative memories. It's a one-layer neural network in the sense that all units are input-output. So there are no hidden units, and there is no distinction actually between input and output. So you input, you set input values, and then you calculate new values, which becomes the output. It's fully connected, which means that all nodes, all neurons are connected with each other, and the weights are symmetric. So going from A to B has one weight, and going from B to A has the same weight. The units are modeled, inspired by the McCulloch and Pitts neural model, which is very simple, with output values -1 and +1. There are two modes, so either you can update the states synchronously at the same time, or asynchronously in some sequences. The weight updating is inspired by Hebbian learning, so it's clearly in the tradition of associative networks. It also has an energy concept, which is very important, that ensures the convergence towards a stationary state. So primarily when you search for a stationary state, you use the value of the energy variable as your guideline. And the models enables fixed point stable attractors, which means which correspond actually to the local minima. And Hopfield networks were invented by John Hopfield in 1982. Let us now look at the updating of a unit in a Hopfield network. So in a Hopfield network, first of all, we have what one could call one-shot learning. That we, in a way, decide how many data items we would consider. Let's say n of those, which corresponds to, one can say, with the memory terminology, how many memories do we want to store in our associative memory. And having decided that, we will construct a matrix X with these data item vectors as rows. And then the weight matrix will be the transposition of that matrix multiplied by the matrix itself divided by n. So we can say it's the normalized value of this matrix multiplication. Okay, so that's the kind of storage part. Then we will look at a particular test case, and in that test case, based on the test case, we will calculate a new value for each of the states, and that is done according to the formula that the new value of the state is +1 is the sum of all the input states from the other nodes in the network times the weight on the connections from those. If that's bigger than a threshold, then we get a +1, otherwise we get a -1. So the outputs here is in the traditional McCullochs and Pitts. The values of neurons y, and j will converge if the weight between them is positive. Similarly, they will diverge if the weight is negative. So in that sense, we can say that this way of doing it is in the Hebbian tradition. So finally, another aspect of this is when you do the updates, you can do them in two different ways. You can do it in an asynchronous way, where you update one unit at a time, and then you can pick them at random, or you can have a specific order, actually. And then there is the synchronous mode, where all units are updated at the same time, and this somehow requires a central clock to the system in order to maintain. So some people think this is less realistic, but because in nature, the corresponding systems in humans and animals and so on, there is actually no global clock of that kind. But actually, we are building artificial systems, so maybe that's not a strong criticism. Hopfield Networks has one very important feature, and that's the energy value. So this is a scalar value associated with each state of the network. And that is defined on the slide. So you can see it's the total sum of all combinations of all states and all the weights between them, divided by -2. Plus the sum of the states multiplied by the threshold. So I will not prove to you the inference of this formula. I will simply say that the setup of this formula, called energy, is that it should ensure that this formula always will decrease over time through the updates. So repeated updating will eventually converge to a state which is a local minimum in an energy function. So if a state is a local minimum for the energy function, it is a stable state for the network. So actually what you can possibly do is that you build a practical Hopfield network system, and then you can store a number of cases defining the network, and then when you for every test case you test, you can look at the energy value, and then you can see how the energy value behaves. And of course, the idea here is that you want to minimize the energy value. The lower the energy value, the closer you are to a stable state. Let us now quickly look at a few graphical examples. So first here, you see a 2-neuron Hopfield network characterized by 2 stable states. You see graphical descriptions of the basins and the attractors for those stable states. If we move to 3 states, you can also see some graphical depiction of that, and you can see that in this particular case, given the details, it turns out that this example have two stable states. And finally, if we move upwards, it's not so easily to depict, but you can have a 5-neuron Hopfield network with a more complex weight matrix, but of course you can also imagine a landscape actually defined by the arrow function in this case. So of course, the more complex the network is, the more valuable the energy function becomes, because it's a simple scalar measure calculated from the system. So even if the system is complex to overview, the scalar, the energy value will always tell you something. Let us now look at a small practical example. So we have a small board with four items on the board, or places on the board. We call them 1, 2, 3, 4, and so there are 2 stable. So for each position, there is either a -1 or a +1. So the orange or yellow here are positive, and the red one is negative. So if all positions on the board are in one of these states, we can say it's stable, because those are the states that can be generated actually by the updating function. Of course, we can introduce externally other states, and these are depicted as blue here. So you can see down here that these items are blue, which means that they're neither -1 or +1. So in this example, you can depict it in various ways. You can depict the graph. Of course, it's very important to understand what the weights are, and as been said earlier, do the weight updating in one shot. So you look at the 3 patterns. We have 3 patterns above, as you see. And actually, in the Hebbian tradition, the updating is based on the average correlations across the 3 patterns. So if you look here for P1 in the column below, you can see that if you compare state 1 with state 2, it's the same, so it's a positive correlation, so you get a 1. If you compare it with the element 3, it's also positive, but if you compare it with element 4, it's the opposite, so therefore it's negative. So this kind of procedure you can go through for all these combinations of the first pattern, and then you do the same for the second pattern, and you do the same for the third pattern, and then you get for each weight, then you get a row, and then you take the average of the elements of the figures for the various pattern, and then you get a column with averages. And actually these average are the initial the weights we will use. One can also set up, and we'll see that soon, a weight matrix, and that weight matrix is because it's a definition of Hopfield network that everything is symmetric, everything is connected, everything is symmetric. So this means that matrix need to be mirrored in the diagonal, and the figures we see here in this column will constitute one of the halves, and the other half of the matrix will be the same, and it's not interesting what's in the diagonal bit, because it's actually the relation from a node to a node. And according to the model, Hopfield model, there is no direct cycle. It's only indirect cycles in a Hopfield model. So, so this means that we can then calculate, construct this as a matrix, as I described, and then we can have a test case. So this means that we multiply this matrix with this vector, and when we do that, we get the resulting matrix, but the result, according to the formula, is not just the sum of the multiplication of that matrix with the test case, because it also have to go through a threshold function, and in this case we have make it simple and have the threshold 0. So doing that threshold operation, we will end up in a new value of 1, 1, 1, minus 1, and that can then be depicted, as you see below, with a Bell state consisting of 3 positive and 1 negative in the bottom right corner. If we repeat the same calculation for the same example using the matrix notation we originally introduced, you can see that if we form a matrix from with the original with the input vectors, 3 input vectors we consider as rows, if we transpose that vector, then we get actually our weight vector by multiplying the transpose vector by the vector and dividing by n. So you can see here a step where we form the matrix, the transpose matrix, we multiply them, and we divide by n. So we end up with the matrix to the right, and then we can use that matrix. So essentially, when we will then want to calculate an updated state, we simply can multiply the new test case with that matrix to get the result. By that, we got a more schematic, better scheme to easily calculate new states based on the weight matrix. Finally, you can see here the alternative way of updating. So in the last case we treated more in detail. We looked at the asynchronous case where all the nodes were updated in parallel, providing that there was some mechanism to synchronize that. So here you can see an example of the asynchronous case where we have to take it stepwise. So first we update one node, we look at the result, we update another, and so on. And eventually that also will lead in the bottom right to a stable state. So by this, we take a little break and come back in part 2 in another video to the same thing. Thank you.